Welcome back. So this time I'm going to look at what the validity of the fluid equations are. So fluid equations and any equations are only valid for a certain range of parameters, and this is true for almost any model. And so here we're going to first look at what kind of things we're interested in. Why would you use a fluid model, and what kind of things are we interested in solving? Then we'll look at what's going on at the small scale. So when are we missing physics? So when is something happening that we won't capture with a fluid model? And this involves things like the distribution of velocities that the individual particles have, and the collisions that happen between them. And then at the end, we'll get to a number which characterizes how valid the fluid equations are. And this is one part of it, but it's an important part of the fluid model validity, called the Dudson number. And this we'll use many times later in the course to derive equations and to test whether our models are valid or not. So I'll start by looking at what are we interested in solving. So what kind of typical time and length scales. And this is looking at things like the frequencies that we want to measure, or the size of the objects that we want to solve for. So if we're looking at waves in a fluid, for example, they might have a typical frequency or a typical wavelength. And so we can use that to try and say which waves can we calculate accurately with a fluid model, and which waves can we not. So we have typical time length scales. So we have some kind of wave. So this is some kind of spatial direction. We call this x, and we have a wave in the fluid. So this could be pressure that I'm plotting here, or it could be velocity. Let's say it's pressure, for example. And it has a wavelength, which is here. Yeah, I'm just going to call it L. So this is L here is a typical length that we're interested in. This is the large scale system size, so we're solving for a wavelength. We want to know how fast is this wave moving, for example. What's the dispersion relation? So this is the size of scale that we want to solve for. So this is for waves, for example. And it might have a length, so a length L, might have a frequency, for example, say omega. So F for a frequency, omega for angular frequency, so radians per second, and then that would give us a time scale, which is just 2 pi over time scale t, which is just 2 pi over omega. So we have typical length scales and typical time scales that we're interested in calculating. Similarly, another kind of problem we might be interested in is a flow of fluid through a pipe, or flow past an object like an aircraft or a car, for example. And so we might have a stream sort of flowing past an object. So a classic example is a cylinder, where you might have a fluid flow that kind of goes around the cylinder like this. We might have a flow like this. So we have a fluid just flowing in and then going around. So this is kind of fluid flow. And here we have time and length scales as well. We have a typical kind of size for this obstacle, or if it's a pipe that the fluid is flowing through, it might be the width of the pipe. And we have a velocity, so this has some fluid flow velocity. This is like a flow speed. So flow speed U, have a size scale L, and this again gives us some kind of time scale. So we have a time scale T, which is just L over U. So whatever kind of problem we're interested in looking at, we can say these are the typical length scales we have, and these are the typical time scales we have. And what we can do is then we can compare these to what's going on at small scales. So what's the microscopic properties of the fluid? So if we look in at really small scales inside the fluid, see what happens here. So we have a microscopic, only one C in microscopic. Okay, so we have microscopic scales, So if you look at really tiny scales in the fluid, so we take a small box of fluid. At really small scales, fluid consists of individual atoms or molecules. And in the fluid approximation, we've assumed that this is just a continuous smooth fluid. So it's smooth everywhere. So we've made the assumption that this is just a kind of smooth fluid with a density and velocity at all points in space. And so here we have something which is discrete. And here we have something which is continuous. And at small scales, if we zoom in on a fluid, small enough scales, we'll start to notice that this is not continuous. We'll start to notice the lumpiness of the fluid. And this will happen when this kind of distance here, so you have a typical separation d, for example, the typical distances between the atoms and molecules. So if the length scales we're looking at become comparable to this, then we'll certainly start noticing that the fluid is not continuous everywhere, but it has lumps and it has individual atoms and molecules. So if the distance between the atoms and molecules is small compared to the sizes we're interested in, like the size of the obstacles or the wavelengths, then making this assumption is generally okay, that we're smoothing over all these little particles. Whereas if we look at really small scales, we'll start to notice these small distances, we'll start to notice the lumpiness of the fluid. And so for the fluid approximation to be valid, we need, at a minimum, we need that this distance should be much smaller than the length scales we're interested in for fluid to be valid. As I'll see shortly, this is not the main thing we need to take care of, but this is at least a minimum requirement. Okay, so the main thing that actually makes a big difference is the distribution function. So it's if we look at all the particles in this box, they will have a range of different speeds, and they'll be bouncing around the box at different rates. And if we look at their properties, a lot of their properties depend on what range of speeds they have. So how many particles have a particular speed in that box. And so what we could do is we could basically count the number of particles with a given speed. So we calculate a kind of histogram, if you like, of particle number versus particle speed. So if this is particle speed or particle energy, for example, so we plot like energy of each particle, and then we could say, okay, how many particles have that particular energy, and we can calculate like a distribution function, so basically a kind of histogram. It might look something like this. So we have some kind of range of energies, and we have the size of this box is like, this is delta E. And so we could count up the number of particles in this box and say, okay, how many particles have a particular energy, and we get a range of energies like this. Now if you now make the size of this box smaller and smaller, so you divide up the number into smaller and smaller bins, the number of particles in each bin will get smaller and smaller. But what you can do is you can instead plot n divided by delta E. So it's the number of particles per energy length, or per range of energy, and this is E, it's energy again. And so now as you again take a histogram and make this histogram smaller and smaller, what happens is it goes towards a continuous function. So as you make the size of these bins smaller and smaller, you end up with a smooth curve, actually like this. And this is called the distribution function. So this function that we plotted here, this is basically f. We call f of e. This is the distribution function. And it means that the number of particles in any range of energies, so the number of particles in a range of energy is f at a particular energy times the range size, so times the range of energy that we're looking at, so delta E, or little de if we're looking at a small range. So this is actually a density, probability density. and so if we add up the number of particles with particular n, with particular energy, and of course if we integrate it over the entire range of energies, we get the total number of particles in the box. So this distribution function tells us something about how the particles are moving. So if you have a particular energies of particles or particular populations of particles, we'll see. Now these, in principle and in general, these distribution functions can have many different shapes. So you could have functions where f has peaks. For example, you could have a peak here, and then you could have another peak here, for example. You might have two different distributions of particles. You might have this might correspond to something like a beam. So if you have a very fast beam of particles which are going through a background gas, for example, it might look a bit like this. One that comes up in fusion plasma applications is a kind of slowing down distribution. So if you have particles which are coming into the system at particular energy, and then colliding and slowing down, you end up with basically a peak at high energy where the particles come in, and then a decaying distribution like this as particles slow down and join sort of the low energy tail over here. So you can have all kinds of weird and wonderful distribution functions. But what we're doing with the fluid is we're making an approximation so that we can describe all of these things instead as just three numbers. So we're saying we have a density, we have a velocity, and we have a pressure. So in a fluid approximation, so we describe describe this f as by using only so either the density, mass density, or the number density n, the average flow speed, and the pressure, for example, or the energy. So we have a fixed number of numbers, and there are fluid equations which have more equations, but the same principle holds. So we have a small number of quantities that we're evolving, and some distribution functions we can approximate and some we can't. So if you have simple distribution functions, I'll see what I mean shortly, then this may be okay. But if we try to describe the shapes of these distribution functions with only a small number of parameters, then we're going to have difficulty, and it probably won't be able to describe these more complicated cases. So what distribution functions can we describe? Well, one of them is the Maxwell-Boltzmann distribution. So Maxwell-Boltzmann, and this is the distribution function you get when you have lots of collisions. So it's a relatively simple distribution function where we have this kind of form here. So if you have energy, we have the probability of distribution function f of e looks like this, and this has a particular form which we can write down. So we have so f of e is just 2 root e. So we have e over pi 1 over kt, 3/2, and then the important part is we have this e to the minus e over kt, where k here is the Boltzmann constant and T is temperature in Kelvin, and E is the energy in joules. So this, you may recognize this as the Boltzmann factor. So if you have multiple different states in the system, this assumes if you have, this is if you have a local thermodynamic equilibrium, then the probability of being in different states is related by this factor here. So if this is true, we have something called local thermodynamic equilibrium. And the important point is that this is basically characterized by, in this case, only one parameter. So we have here is temperature. So the energy distribution just depends on one parameter, which is the temperature here. And if we plot the velocity, for example, so this would be the distribution function as a function of the velocity. What we end up with is, if we have here, this is say the velocity in the x direction, so I'll just plot one of them for now. We end up with a distribution of different velocities, which basically has a Gaussian kind of shape. And so here we have f of, so the probability of having a particle with a particular velocity in the x direction looks like a Gaussian. So we have so fb is given by, so we have an m over 2 pi kt half, and an e to the minus m over kt. And then here we have a vx minus the average speed squared. So it's like an e to the minus this velocity squared. And so the peak of this distribution here is the average. So this is the flow speed. So this is when v of x is equal to u. And then there's a distribution around here. And this width depends on the square root of this parameter, so it's proportional to the square root of t. So we have a width of the distribution function, we have a mean, and we have, of course, the total number of particles gives us the density. And so here we have three parameters that we need. We need the total area under the curve, which is the density. We need the mean, which is the flow speed, and we need the width, which is the pressure or the temperature. And so here we have three parameters, so which is basically rho, u, and pressure, which then gives us temperature. So using the three parameters, we can describe a Maxwell-Boltzmann distribution, and it's these three parameters that we solve in the fluid equations. So when do you get Maxwell-Boltzmann distributions? Well, there are many ways of deriving Maxwell-Boltzmann. You can get it from small-scale statistics, so Boltzmann statistics. There's something called the H theorem that again is a way of deriving it. You can maximize the entropy, is a quite nice way of doing it. So it's the maximum entropy of a system given a fixed number of particles and a fixed amount of energy. One other way of getting it is that you can look at the collision operator, if you've done kinetic theory, and the equilibrium solution of the kinetic theory collision operator is again the Maxwell-Boltzmann distribution. So it happens when you have lots of collisions, so when particles are bouncing off each other and exchanging energy frequently. So Maxwell-Boltzmann, let's see, basically is the solution when there's lots of collisions, or many collisions. So if the particles inside a small region are colliding frequently with each other, they exchange energy and they reach some kind of equilibrium where the energy is shared between them in a Maxwell-Boltzmann distribution. If you have, say, a population of particles coming in into that region, it will take some time for them to collide and share their energy. And in that small time before collisions occur, you'll have two very different energies. For example, you might have a case here where you have a distribution function where you have, say, a cold gas, and then here we put a beam of particles. In the time it takes for the collisions to occur, we have a very different distribution function. It's not Maxwellian, and we couldn't describe it with the fluid. But when collisions occur, these particles will collide with each other and share their energy, and they will very quickly, on the timescale of these collisions, approach a Maxwell-Boltzmann distribution. And so the key parameter is that the collisions occur frequently compared to the timescales that we're interested in. So we require one frequent collisions. So collisions occur much more frequently than the frequencies we're interested in, or much faster than the timescales we're interested in. So if we had omega as the frequency of the waves we're looking at, shorter time than the timescales we're interested in, for example. So they have to go very fast. So we write down the collision frequency, we call omega c. So this is the frequency that particles are colliding. So a given particle inside the gas, how often does that particle, on average, hit another particle? And that has to be much, much bigger than the typical frequencies we're looking at. And in air, for example, e.g. air, this collision frequency is extremely large. So nu c is around 10 to the 10 hertz. So extremely often particles are colliding with each other, and so in practice this is not much of a limitation in air. There are cases in plasmas, for example, where the collision frequency can get small compared to the frequencies we're looking at, and so there this is something we need to take care of. So the other thing is that the distance that particles travel. So if you have say two regions, one hot and one cold, if particles can travel straight from the hot into the cold, then that is going to give us distribution functions which don't look Maxwellian. So very quickly depart from Maxwellian. And so we need that the particles have many, many collisions in the distance as they travel from one point to another. And so the distance between collisions, which is mean free path, so lambda mean free path, and that has to be much, much larger, much, much smaller than the length scales we're interested in. So this has to be much, much less than L, where L is the length scale, where L is the length scale of interest. So it's the wavelength of the waves, or the size of the obstacles or pipes, length scale of interest. And this gives rise to a parameter that's used to characterize this. So is the Dudson number. So this is an important parameter for fluids. So it's labeled Kn. And this is the ratio of these two. So it's lambda mean free path divided by L. And this has to be much, much less than 1 for fluids to be valid. So this has to be very small compared to these lengths. Now typical values, so for example air, lambda mean free path is about 68 nanometers, also at atmospheric kind of sea level, so 68 nanometers. So for air, for example, unless you're trying to study extremely small length scales or extremely high frequencies, the Dudson number is usually very, very small, and so the fluid approximation is usually a good one. For plasmas or rarefied gases, so if you're looking at the top of the atmosphere, these mean free paths can become very long. So in plasmas these could become meters, for example, or tens of meters in some cases. If you're looking at, for example, electrons or scattering along the scraper layer or the high temperature regions in the core, then these can become large compared to the length scales you're interested in, and so this approximation can start breaking down. So this number we'll use several different places to understand when fluids are valid and when they're not. Okay, thank you. See you next time.